Hello, it's Keith here, and this is lesson 14 of the Suck Hunt series of Z80 programming tutorials. We're making my little Suck Hunt game, and you can see above me we've got the Spec Next version showing off its somewhat amazing intro. It amuses me if nothing else. And we're missing the title screen. Well, why is that? Well, we'll fix that. I wasn't expecting to do this, but basically it has two banks of data that the game needs, and one of the banks has become corrupted by another piece of test code, so we just need to compile that. I've used the wrong run command, that's why. So that will compile the first bank there, and then if we go here and we compile again, this time with the correct option of bank 2, the game should now run correctly. So there's the title screen again, and hopefully after the title screen finishes we will see the introduction screen. And basically this is a parody of Operation Wolf. So basically you will now have the Operation Suck speech, which is again the parody of what Operation Wolf did during its title screen. It just amused me to make fun of stuff and have my little characters do the Operation Wolf loadout introduction. Anyway, the game is of course actually a Duck Hunt style game, which is hence the title. And today we're going to be going over the code that handles showing that introduction sequence and the title screen. I thought it was a bit of fun, and hopefully if you're writing your own games, maybe you'll get some ideas of things you might want to do. And if I've done a bad job, maybe you can get some ideas of things you definitely shouldn't do. Whichever happens, let's go over to the source code and let's take a look. Okay, so the graphics for the title screen and also the intro graphics, those quarter screen images, are done as little tile maps. And as said last time, basically we're using 1 byte per tile, so these are tile 0. But if we go over tile 255, we use 2 bytes. So 255 plus 96 is that tile number. That's how we do it. And it's just to save a byte for the low tile numbers, but to still allow us up to 512 tiles. The reason we use up to 512 is because that's what the Sega Master System can do. It's got a limit of 512, actually slightly lower. But anyway, as I say, that's why we're using a hard limit of 512 as our maximum. Now, the title sequence is a sequence of 4 corner graphics in the 4 corners, and there's 2 animation frames per graphic. So we've got this list sequence here, which is defining the corner, the color, and the 2 frames of animations. So here we've got the X position, the Y position, and also the color, and the color is going to be a 1 or a 0 here. And so these are the sequences and the frames of animation there, and we'll see all of that later on as we look at the code. So let's go to the top here and let's take a look. It's actually quite handy that bug happened where the title screen didn't show, because that's what will happen if we don't define our 2 banks correctly, and we'll see that bank switching code later on. So here is our introduction start here with this enable intro. I was disabling it during testing because I hadn't written it yet. We load in our introduction song here. We've got a different theme, which is again hopefully pretty similar to the Operation Wolf music. And then we're loading in our animation list here. We load in the X and the Y position to show the little tile map. We load in the memory address of the tile map. We transfer that into HL. And we use show tile map alt pos quarter intro. A little bit of a long title there, but basically it's a quarter size tile map at a specific location. That's what it means by alt position, a specified position. We then load in our color here, and we are just doing our fade routine here, which will fade to the correct color. Now, we're using these little do EIs, and we've got a do DI occasionally we might see. And what this was is during the development, I didn't know what circumstances I was actually going to use interrupts for. I hadn't decided how I was going to do them yet. Now, how I ended up doing them was using interrupt mode 1. And basically, I never disable interrupts. So I've got that disabled. I do disable them on some systems, but the problem with the Spectrum systems is a missed interrupt never occurs. And so if you disable interrupts for a short period and enable them, your music will slow down in that time. On a system like this, the Amstrad CPC or the MSX, the interrupt will fire as soon as you enable interrupts. So disabling interrupts is fine on those systems, but on the Spectrum it's a problem. So that's why you will see those weird macros do EI and do DI rather than enable and disable interrupt commands. But that's just how that works. So we show our first tile map here. We then do a fade in and we pause a little while to show the first frame. We then load in the second frame, and we show the second tile map over the top of the first one, a longer pause, and then we fade out again, and that will finish the animation, and we repeat for the next sequence, and so there'll be 4 in total for the 4 corners there. So that's the introduction routine, And then what we do next is we want the speech to play. So we're setting the accumulator to 1 to play the speech. We don't play the speech unless we've shown the introduction. You see, if the player has died, the game over screen shows, which is also an Operation Wolf parody. We drop back to the title screen, but because we've not shown the introduction, it doesn't make any sense to play that Operation Suck speech there, because it only makes sense if you've seen the Operation Wolf introduction. So the accumulator would be set to 0 if we don't want to play the speech. We're then resetting the stack pointer to our default position because we're starting a new game, so we're setting everything back to the way it was. Clearing the screen, setting the colors to black, and then what we're doing is we're loading in the current state of the 3D mode. If the 3D mode is in 2D, we're going to jump to down here and we're going to set accumulator to 4. Otherwise, we're setting the accumulator to the palette number. Well, why are we doing this? Well, unlike the Amstrad CPC, the Amstrad CPC version had 2 different versions of the title screen, a 3D version and a 2D version. That was a 4-color system, and the tile map was basically 4 colors in black and white mode, but just 2 colors per eye, black and white per eye, because we lose a lot of the colors to get the 3D effect. The Spectrum Next doesn't have that problem. It's got 16 colors, you can see them here, and so basically the screen will be 4 colors in 2D mode and 16 colors in 3D mode. And the way we do it is we actually remap the colors to effectively neutralize one of the eyes. If you think about it here, if you just think about this part here, if I wanted to convert this to 2D, well, I could convert this blue here to white and this red here to black, and you would effectively disable the red eye by doing that. And that's effectively what we do. We have to do it with all of the shades here, but we have a special palette to do that. Let's have a look at it now, actually. Here it is. So you can see here we've got this special 2D palette here, and you can see we've got 4 colors set to black. We've got 4 colors set to dark grey here. There's 4 of them. 4 colors set to mid grey and 4 colors set to white, and this has effectively disabled one of the eyes. Just as a side note, we do have the proper palettes here. We've got the red cyan palette here, so that's for a red cyan 3D glasses type. We've got the blue, yellow, the so-called color code ones, which I believe their patents are expired now if you're interested. We've got green, magenta there as well. So yeah, we've got lots of options there. These are all 1 byte per color palettes. The Spectrum Next does support up to 2 bytes per channel, per color, sorry. But I thought it'd be better to save a few bytes because I had to branch out into a second memory bank to get the game working at all, and the bigger it is, the more problems you end up having. So saving a few bytes on a 16 color palette did seem worth it, even though it's relatively small. Okay, so that's how we're doing our palette. What we do next is we are going to page in that extra bank, and you did actually see it. So I mentioned last time, but basically this is a separate program on the cassette, and what happens is it loads first before the main program, and it loads into memory, transfers in a second bank, dumps its entire contents to that second bank, restores the original state of the memory and returns back to basic, and then that loads in the second bank. And I've got a special build script here. If I just go here, you will see I've got 2 options here. I've got ZX Next Bank 2, which is the second file on the tape, and ZX Next Tap 48, which is bank 1, which is the first file on the tape. And what I did wrong is I compiled this as the first program, so the graphics for the title screen weren't in memory, and that's why the title screen didn't show the first time. Now, when it comes to really wanting to show the title screen, we've basically got the program code in our main bank, and we've also got the tile map numbers, the numbers of the tiles we want to show, but we don't have the bitmap pattern data for those tiles. So what we're doing here is we're going to page them in. We're using the Spectrum Next registers here, and we're basically paging in the extra memory at memory address C⁻0 onwards here. The first 256 bytes are allocated to the actual initialization routine here. The actual tile data starts at 6100 here, so you can see that's just there. It's much easier to have bitmap data at an odd memory location than program code, so that's why I've done that. We're then running our show tile map routine, which will copy the tile map. The bitmap data is at 6100, and the way I page in layer, I'm using layer 2. The way I page it in is from the 2000 to 3FFF range, leaving the low memory area for my interrupt handler and the rest of the memory area for my program code, and in this case the pattern data. So that's how I do it. we then page in the regular memory, so the rest of the program code comes back in. We fade in and we set our palette. Now, I can't actually remember what is at the end of the program code here, because of course it's possible that parts of this will be paged out. So yeah, basically we've got our game sprite data here, got our sprites here, the operation suck speech here, that's not going to be needed showing our title image, the font, that's not needed while showing the title image, cursors. So a lot of stuff at the end of the program here, which is probably going to be paged out while that title screen is showing, but nothing that's going to cause a problem for that code. I do all of the thinking through the paging myself. You can get some assemblers that will kind of handle some of it for you, but I tend to be a bit brutal on it, and I tend to do all the mathematics of it myself, and often, like in this case, I've defined manually the memory address of the bitmap data. So rather than getting the assembler to do any calculations for me, I'm taking responsibility for it myself. As I say, some assemblers can actually deal with bank switching for you. If you want to do that, I'm not saying that my way is better. This is just the way I've always done it. So, you know, do it whatever way works for you. Anyway, once we've shown the title screen, we're then setting the correct palette here, that's 3D or 2D depending. We're then just locating for the high score, and we're also showing the key mode. Now the Spectrum Next version can use a Sinclair joystick, which uses the number keys, or it can use a Kempson mouse. So we can actually use the Kempson mouse as well, because the game does work best with a mouse, to be honest. So there we go. Now we're going to look at the title screen more next time. What we're going to look at next though is the routines that handle the 3D switching and the palette, because I think they're quite fun. Okay, so when we are switching 3D modes, we're loading in the current depth state. If the depth is 0, then we're setting the 2D mode, otherwise we're setting the 3D mode. So that's just going to set the correct current mode. We have the change 3D mode, and what this does is it toggles between 4 possible depths. Depth 0 is off, 1, 2 and 3 are different stereoscopic depths, because the distance between the two eyes increases the 3D effect and gives you a good headache as well, which is possibly what we want if we're playing with 3D. So we're increasing the current 3D depth, masking it between 0 and 3, setting the new 3D depth, and then we're setting the settings accordingly. Now, the way we actually turn off the 3D is we use self-modifying code. There are 2 eye drawing routines, which you saw last time, show sprite L for the left eye and show sprite R for the right eye. We're turning off show sprite R by putting a byte C9, which is a return command in bytecode. So we're putting a return at the start of show sprite R, turning it off. So that will turn it off. The way we turn it on is we actually read in a copy that we took at the start of the program, which will be the correct command that was supposed to be there, and we put that in the correct position. So that will restore whatever byte was there originally, which is probably a load command or something like that. It doesn't matter. But by loading it at the start of the program, we've absolved ourselves of having to worry about what bytes should be there for normal running. The code will work that out for us. Okay. Now, when it comes to setting the palette, we have a possible 4 palettes, 3 3D ones and that special one for the 2D mode. And basically what we do here is we are going to take the palette number, and then we are multiplying it effectively by 16, because there's 16 bytes per palette, and then we're loading the base for the palettes, adding the offset, and then what we're doing is we're transferring 16 bytes to the palette, and we're using NextReg hexadecimal 40 to select palette index 1, reading in bytes, and then sending them to NextReg 41, which will set a single byte color. We're repeating that 16 times to set our palette. There is an alternative version which will just set 4 palettes, and we will see why in just a moment. Okay, so we saw those 16 color palettes before, but there are some alternate palettes that are just 4 colors. These are the fade palettes. Here they are. Now you can see lots of entries here, and you might think, well, there are 16 there, but actually this is 4 sets of 4. There were 4 stages of fade from off to maximum. There are actually 4 stages here. So this is a fade out. So the first one is fairly bright. The second one's mid-range. The third one's fairly dark, and the last one is switched off here. The fade-ins are the opposite. You can see there. Now at the end stage of these, we do actually either clear the screen or restore the true palette that should be enabled. So we've only got 4 palettes there, and we use those as part of a sequence here. Now when we want to do a fade, we've got a few options here, and so we've got our do fade in and do fade out routines here, and these are actually used during our introduction. Now you remember that we were setting the accumulator during the introduction, and it was a 1 or a 0, and what we're doing here is based on the accumulator, we're potentially swapping DE and HL, and this allows us to select what color, either pink or blue, that the particular fade will be, and that's how we get the effect during the title sequence. So what we do at this point, we've got the HL pointing to a palette that we want to show, and that palette will contain 4 entries times 4 for the 4 stages of fading. So what we're going to do is we're going to set the first 4 colors to those palette entries, but we back up and restore HL. Then we use the same 4 for the next 4. So now we set 8 palette entries, and then we do the same. Now we set 12, and then we do the same. Now we set 16. So we set all 16 colors to the same 4 colors. We then delay a little while, decrease and repeat our B counter. Our B counter is set to 4 because there's 4 stages to the fade. And then we repeat back up here with the next 4 stages of that fade. And so basically, the first time it's run, we will use this line here, and then the next time we would use this line here, and then the third time this line here, and then the 4th time this time here. And so those 4 entries will be repeated for all 16 colors, and so that's how we're using that. And again, it sounds silly, but you know, this 16 bytes is a lot for palettes, so you know, you want to kind of reduce it as much as you can, and so it was an easy way of reducing the amount of memory to use the same 4 bytes 4 times during this fade routine. And that's how we get the introduction there. So there we go. As I always say, you can go to my website and you can download the source code for Suck Hunt, and you can also download the built game from the Suck Hunt website. So if you want to get the game, go ahead, go and get it. And as I always say, you're welcome to do anything you want with the source code. Take bits of it out, put them in your own games. And if you manage to make commercial games from that, good luck to you. You're welcome to do so. It's there as an educational thing. It's not really there as an amazing game because it isn't one. It's just a bit of fun. Anyway, I hope you've enjoyed this. If you have, you can welcome to buy my book. It's called Learn Multi-Platform Assembly with Chibi Akumas. Covers Z80, 6502, 68086 and ARM. And it's available now from Amazon, print or digital. And if it's a success, which it is already, I will make another book in a year or so, which will cover some more CPU types. It's done very well. So yeah, that's pretty certain that there will be another book coming up later on. Anyway, I hope you've enjoyed this. Thanks for watching today, and goodbye.